All right. So in our part 4 of the lecture video, we want to look at the trial question, okay? And that is we want to start with question 6.1. Exactly. So our question says that a 400 long bar has rectangular cross section of 10 by 30 millimeters. This bar is subjected to I 15 kilonewton tensile force on 10 millimeter by 30 millimeter face. Also, it is also subjected to 80 kilonewton compressive force. So you can see the keywords that they are using over here. We saw tensile force, and I told you in lecture 3 that anywhere you see tensile force, you know it is a positive one because of the direction in which it is facing. Okay. But for the compressive force, it is a negative force. Okay. So the tensile forces, I'll highlight them with yellow ink, but the compressive force, I'll highlight it with a blue ink just for you to see the difference. So let's proceed. The bar is subjected to 80 kilonewton compressive force of on 10 millimeters by 400 millimeter face, okay, and 180 kilonewton tensile force on 30 millimeter by 400 millimeter face. Now we are supposed to find the change in volume, okay. We're supposed to look for the change in volume. That is what we don't know. All parameters have been given. So now, if our elasticity is equal to 2 times 10 exponent 5 Newton per millimeter squared and Poisson ratio is equal to this, we are supposed to calculate for the volumetric strain, and that is the problem of the day. Okay. As we are using this as uh, our formula of steady, good. For which, due to the direction of this, we can say that this is our Z. The 180 kilonewton is our Z. Okay. And also our Y, okay, is this 80 kilo Newton. And there's and the which one? The X become the 15 kilo Newton. So this is the X. Okay. So if you are using this as let me say our formula, then we can look on this to just calibrate it so that in solving the problem, life can be much more easier. At the end of the day, after solving, this is what we are supposed to what? Get. Okay. I'll urge each and every one of us to write this somewhere. Put this down somewhere. You're not supposed to forget this. Okay, because if you are being given the question and you are able to identify X, Y, Z, then at the end of the day, you realize that the problem you are about 60% solved. Okay. So let's see how we can be able to pull down our given and make history. So let's quickly pull down the given, but first of all, we try to draw the diagram. Then from there, we can use it to pull down our given, and then we see how best we can proceed. Exactly. Exactly. But take note, which kind of force is acting on this body? Because yesterday you realized that we studied case 1, case 2, and also case 3. Okay. So which of the cases do you think will apply to this? Which of the cases do you think will apply to this? Better still, we can go and investigate for ourselves to know. Okay. Let's go to case 2. I believe case 2 best explain this. And let's go to case 2 to see if that is really truth. You see, this is the case 2. And this is what I'm talking about over here. You see. So case 2 is just about the volumetric strain of rectangular. And the diagram we're having is a rectangular one. Okay. Case 2 is just talking about, this is the case 2. Okay, so this is case 2. And case 2 is actually talking about the volumetric strain of a rectangular bar subjected to a force in three mutual perpendicular direction. Okay, so this is a force that is subjected to three mutual perpendicular force in a particular direction. So you see that at the end of the day, the formula that we can use to get our volumetric strain is this. Okay, we have to use 1 over elasticity multiplying the stress at x plus stress at y plus stress at z, or into bracket, still multiplying 1 minus 2 times the Poisson ratio. Okay. So let's see how best we can use this idea to solve our problem. Okay, so let's quickly go and pull down the given. Let's quickly go and pull down the given. Okay, so this is my given over here. Good. So first of all, we know that our question that we are having, the problem we want to solve, or the problem we are solving. Yes. So we were told that the length of the bar was 400 mm. Okay, and it has this. So let's quickly put that down. So this is it over here, and then the length. So we say that our length of the bar, okay, the length is equal to 400 mm. Good. And the cross section we saw over here, you see that the cross section 10 millimeter by 30 millimeter. Okay, so let's put that down. This is the cross section. That is the 10 millimeters by 30 millimeters. Okay, so this is the same as the L you are seeing over there. Let's go back to our question. So they say a 400 long bar has rectangular cross section 10 millimeter by 30 millimeter. This bar is subjected to 15 kilo Newton tensile force. Okay, at this face, that is the 10 millimeter by 30 millimeter face. Okay, so I told you this is going to be a positive, this is going to be negative, and also this is going to be hot positive. As simple as that. So let's quickly put that down in our given and see how best we can proceed. So load in x direction. Let's quickly write down the load in x direction. And this is the load in the x direction. Because if you study from the diagram, you see that the 30 millimeter, the 10 by 30 millimeter face, where can you locate it? This is the 10. Okay, that is the 30 millimeter face. So it is as simple as that, and that is the x face. Okay, so let's just quickly represent it that way to just make life easy for us. So this is the hot load, load at x direction. So if we want to be more logical, we say that load in x direction. That is the load in x direction is equal to what? 15 kilonewton. Okay, 15 times 10 exponent 3 Newton. And it is a tensile force. Okay, so I can write over here, it is tensile. Good. Also, let's put on the load in the y direction. So let's write here load in y direction. Load in y direction. Load in y direction. And the load in y direction, let's go and look for it. That is actually the 80 kilonewton. Okay, so this is the load. This is it. Load in the y direction. That is it. Okay, and that is the 80 kilonewton. Okay. So the given attract marks. Okay, the given really attract marks. So it is always important to do it, even if you are not able to do anything and you're able to put down the given. You can never get zero in this course. Okay, so if you get zero, it means that you don't attend lectures. Okay, so we want to write the load in the y direction, and that is the compressive force. Okay, you can see that it is moving towards it, so it is compressive, and that is 80 kilonewton. Okay, let's quickly put that down. And load in y direction is equal to 80 kilonewton. So that is 80 times 10 exponent 3 Newton. Okay, I'll put that down later, and that is compressive. Okay. So into brackets, compressive. Okay, exactly. So what are we going to do next? Let's now put down the last one. That is the load in z direction. So load in z direction. Load in z direction. And that is the 180 kilonewton. That is the last one. I'm sure we all know. That is 180 times 10 exponent 3. Okay, Newton. So this kind of load is also in what? Tension. As we can all see from the question over here. The 180 kilonewton is also moving away from the bar, and that is the Z. Okay, so we are saying that load in Z direction. Better still, to make meaning and understanding more better, I could write it this way. This is X, Y, Z. Okay, so at the end of the day, this is the tensile. So it's a tensile load that was being applied. Okay. uh So let's quickly put down the elasticity and the Poisson ratio, and let's begin to solve our problem. So our elasticity, our elasticity, our elasticity now is equal to what? E. Okay. Which is equal to 2 times 10 exponent 5 Newton per millimeter squared. Newton per millimeter squared. Exactly. Okay. Now your Poisson ratio. The Poisson ratio. And the Poisson's ratio is giving us this. Okay. And that is 0.3. This should tell you that it's a still. So from here, we are supposed to calculate for the change in length. We are supposed to calculate for the we are supposed to calculate for the change in volume. Okay. We are supposed to calculate for the change in volume. So we know that the volumetric strain is equal to change in volume over the original volume. Okay, but first of all, we have to go and okay, so from there, let's quickly try to put down the diagram. Okay, to make life much more easier, let's also try to put down the diagram quickly, so that we don't lose the marks for that too. So let's put down the diagram. Then from there we can solve the problem. Okay, so this is the diagram I want to put over here. Yes, so this is our diagram you're having over here, and the one moving in the direction of the Z was 180 kilonewton. Let's quickly put that down. 180 kilonewton. Okay. You will also denote it over here the same way. 180 kilonewton. And the one moving in the direction of X, okay, is 15 kilonewton. This is our 15 kilonewton. Exactly. We quickly come and put the same thing over here. 15 kilonewton. You see. So as simple as that, as simple as A, B, C. Take note, I want to use a different color pen to write that for you to see. Oh, the distance from here to here is what? 10 millimeters. Okay, 10 millimeters. So that is it over there, 10 millimeters. 10 millimeters. Okay. And also the distance from here to here, like this, okay, is actually 30 millimeters. 30 millimeter. And the length of the bar, which I think we all know, the length of the bar, okay, that is from here to here. Okay, the length of the bar. The length of the bar itself is equal to what? 400 mm. Okay, so I hope we all know it was given in the question as simple as ABC. Okay. So let's quickly proceed from there. Let's quickly proceed from there. Let's quickly proceed. So that implies that now that we know most of the sides, we can proceed. Okay. So this is it for these two. As simple as that. So let's just continue from our solution and see how we can get our answer. So this is my solution over here. This is my solution. Exactly. Okay. So we proceed. But we know that our volumetric strain, in this case, the formula I'm going to be using is what? 1 over E. Okay. Multiplying the stress at X. Okay. Multiplying the stress at X. Multiplying the stress as X minus, you see that the stress as X was a tensor one. So that is why we are going to use positive. But the stress at Y, because it is compressive, is going to be negative. Okay, so from whatever we learned in lecture, we will draw that idea back here. Yes, that is analysis of uniformly varying bars. Okay, so quickly go and read that, and life is going to be much more easily. So this is the stress in the direction of the X plus the last one was a tensor. So that is the stress in the direction of the what? Z. Exactly. Exactly. Okay. And all of this is going to multiply 1 minus 2 mu. Okay. But you also know that this same volumetric strain is also has a different formula that is also known as what? Volumetric strain is equal to the change in volume over the hot original volume. So if we are looking for this change in volume, what are we supposed to do? If we are looking for the change in volume, what are we supposed to do? We are just supposed to make change in volume the subject. Okay. And from cross multiplication, if you do the cross multiplication, you realize that finally you are going to get your volumetric strain, okay, to be equal to what? You are going to get your change in volume to be equal to what? The volumetric strain times the what? Volume. Okay. So let's all take this very serious. This is what we are going to use to get our final answer. But it will requires that we have to go and calculate for our volumetric strain. That we have to use this formula to calculate for the volumetric strain. Then also we have to come and calculate for the volume of the what? Bar. Okay. In that case, we can use this formula to calculate for the change in volume we are being asked to calculate for in the question. Okay. So first of all, let's calculate for the volume. So let's calculate for the volume. Then from here, we say that the volume of bar. So I write over here, volume of bar, the volume of the bar. Good. So the volume of the bar into brackets V. Okay. Then from here, I can say that my V is equal to the length times the breadth times what? Height. From here, it's just a matter of substitution. Okay. Then finally, we can say that the volume of our bar, what is the length that was given? The length given to us was 400. So 400 times the breadth, and the breadth was 30. Okay. Times the depth, that was what? 10. Okay. Exactly. 10 millimeters. So finally, since they are all in millimeters, our answer is going to be in what? Millimeter cube. Okay. That is, if you multiply all of this, let's all multiply this and see the answer that we are going to get. Let's all quickly multiply this. That is 400 times 30 times 10. And you are going to get 120,000 or 120 kilo. So this is 120 times 10 exponent what? 3. Okay. Millimeter cube. As simple as that. As simple as that. So we are done calculating for our volume. Then from here, we can now go and look for our volumetric strain. This one. Once we look for volumetric strain, we can just proceed. But I realize that we don't know the stress at, we know the elasticity, we don't know the stress at X, we don't know the stress at Y, we don't know the stress at Z. So it implies that we have to also find for all of those. But we know the Poisson's ratio. Okay. So it's just a matter of knowing the area, and then we are good to go. Since we are done with this, let's also come and calculate for what? The volumetric what? Strain. So you write over here volumetric strain. Volumetric strain. Okay. Uh-huh. So our volumetric strain in this case, this is what we are talking about. Okay. Finally, we can still put down the formula and talk plenty about it. So our volumetric strain and the formula we are using in this case is what? 1 over E. Okay. Yes. Times stress at X minus stress at Y plus what? The stress at Z. Okay. Bracket close. All multiplying. All multiplying 1 minus 2 mil. Exactly. So from here, what are we supposed to do next? That is, we can just we can come and look for these people. Okay, so let's look for them. Then later we can substitute them into the equation, and we are good to go. So finally, first of all, let's look for what? For stress at X. So that is for stress at X. So we are going to find stress at what? X. So let's look for the stress at X. And the stress at X, we can say that our stress at X, our stress at X is equal to what? The load at X over the area. So the load at X over the what? Area. And that can simply be dissolved or calculated for by the load at X. What is the load at X? From our diagram we're having over here, you realize that the load at X, let me denote it, let me calibrate it for you to see nicely. And this is what? X. Okay, this is the load at X. This is the load at X. This is the Z. This is the load at Z. Okay. And this is the load at Y. As simple as ABC. As simple as ABC. So don't get confused. Okay. And so the load at X is 15 kilonewton. So let's quickly put that down. 15 kilonewton. So the 15 times 10 exponent 3. 15 times 10 exponent 3 all over the area. So the area at X, what do you think it is going to be? The area at X is just 10 times 30. Can you see? Length times breadth. Okay. It is just 10 times 30. That is this face. Okay. This is the face I'm talking about. If I have to still change a different color pen, I will denote that for you to see nicely. Okay. That is, I'm just talking about this face like this. Okay, so you see that here is 10. Okay, and this long side like this is what? 30. So if you are focusing on this, I will just multiply the 10 by the what? 30. You see? So let's just quickly put that down. So here is going to be just 10 times what? 30. So that is the 10 times 30. So let's quickly point this on the calculator quick and see how best. Everybody, please let's partake. That is 15 times 10 exponent 3. You can punch your answers in the comment section and I'll review them for you nicely. So I'm getting 50 Newton per millimeter squared. Okay. Yes, because this is in Newton and these are also in millimeters. So when they multiply, exactly. So if you multiply this, you're going to get 50 Newton per millimeter squared. That is 50 Newton per millimeter squared. Okay. So that is the answer for our stress at X. Let's also go and look for the what? Stress at Y. This one. Mhm. Let's also go and look for the stress at Y. So for stress at Y, this is for stress at Y. Okay. Better still, we can put it in formula in a bracket so that it can be differentiated nicely. So the stress at Y, this is still the same method. You see, so the stress at Y is equal to the load at Y over the area at Y. Okay, so load at Y over the area. Okay. So this is the area at X, and then this is the load at Y, area at Y. So let's quickly do that. Let's quickly do that. Look at the area at Y. Now we are done with this one, so I can clean it. Uh-huh. Exactly. So now we are going to focus on the load at Y. Okay, and the load at Y, we all know this is it. This face, I mean this time is the face that I'm shading. You see, and this is the load at Y. So if we are focusing on this phase, then what is going to be the area? You realize that the area is going to be actually just 400 times 10. Okay, the 400, this 400 times this 10. Okay, so let's quickly go and do that together. Let's quickly go and do that together. So let's quickly do that together. And this is equal to 80 times 10 exponent 3. Okay, so 80 times 10 exponent 3. Okay, all over 400. 400 times 10. Okay, so quickly. If you all point this together, what are we going to get? That is 18. That is 80. Okay, 80 times 10 exponent 3 over 400 times 10. Exactly. You are going to get, what are you going to get? You're going to get 20 Newton per millimeter squared. Yes. So some few people got the answer. Solomon had it right. Mr. Darko also had the answer right, and that was so wonderful. Okay, so that is 20 Newton per millimeter squared. 20 Newton per millimeter squared. Exactly. So let's go and do for the last one. In a few minutes time, the link is going to go off. Let's all do all to come back again so that we can complete whatever we are doing. Thank you very much. Also, don't forget to like, comment, and then subscribe to my channel so that anytime I release a video, even if I don't share you the link, you'll be given a notice so that you can always be updated in the world of engineering. If you also find my videos very attractive, don't forget to throw $1 on my name if you happen to meet me in person. Thank you. So let's look for the stress at Z. the stress at Z. So it is still the same formula. It's still the same method. Okay, so that is the stress at Z is equal to the load at Z over the area at Z. Okay, so the load at Z over the area at Z. Okay, so that is equal to, let's go and search for it. So you see, it is this phase. So now we are done with here, and our next place of focus is the area at Z. Okay, yes. So this is it. This is the Z phase. This is this phase we are going to focus on.